Today I'm going to show you how to work through some problems using Dalton's law of partial pressure and explain a little bit of the theory behind it. So you'll be able to explain the behavior of mixtures of gases. I'd like you to go ahead and solve this problem. This uses a combination of concepts we've looked at. So you're given the percent breakdown of cyanogen, which is made up of carbon and nitrogen, gives you the percentages. Then gives you the temperature, 25 degrees Celsius, 751 torr, 1.05 grams of cyanogen occupies 0.5 liters, and what's the molecular formula of it. So take your time, work through this from your notes, and put in an answer. Okay, so to lead you into Dalton's law of partial pressures, you worked through some of the Pogel activity, which deals with doing various calculations to show you that the behavior of gases is independent of one another. So if I have a mixture of gases in a container, the total pressure in the container is the sum of the pressures of the individual components of it. This formula is on your reference sheet. As simple as it is put there for you. So the total pressure exerted in the container is the sum of the pressures that each gas would exert if it were alone. This is the derivation of the Dalton's law from the ideal gas law. So we have the ideal gas law, which is PV equals nRT. So if we're solving for pressure, we can divide by volume, and we'd have the initial pressure of the first gas, the pressure of the second gas, the pressure of the third gas. So I could take all of these, add them together, and that would get me the total pressure. And this would just be really sloppy, so don't even worry about it. But that's how it's derived algebraically. Therefore, for a mixture of ideal gases, the total number of moles of particles is what is important. Okay, so how many particles are in the container tells you what the total pressure is going to be. It doesn't matter what the gases are. So it doesn't matter if I have a mixture of noble gases, if I have carbon dioxide and oxygen and nitrogen and neon. It doesn't matter what they actually are. It just matters how many of those particles you're dealing with. So the fact that pressure is not affected by the identity of the gases tells us two things about ideal situations. First of all, the volume of the individual particles isn't important. So we really just consider the volume of the gas to be the volume of the container. The particles themselves are negligible. They're so tiny. And also it tells us that the forces among the particles are important. So ideally, gases do not exert intermolecular forces on one another, but we'll learn later in this chapter they actually do. So mathematically, I'm going to get you through a couple examples here. So consider the following apparatus containing helium in both sides. Initially, the valve is closed. After the valve is open, what's the pressure of the helium gas? So this is the answer we're shooting for. So we have a stopper here. So there's a couple different ways to solve this problem. I will walk you through both of them. So what we can do here is treat this portion of gas independently of the other portion. So we could do P1V1 equals P2V2. So P1 would be 2 atmospheres, V1 would be 9 liters. The new pressure is what we're solving for, and the new volume is the total volume of the container once I take that stopper out, which would be 12 liters. So the new pressure of the yellow portion of the gas would be 1.5 atmospheres. I could then do the same thing for the other portion of my gas. P1 is 3 atmospheres, V1 is 3 liters, P2 is my unknown, and then V2 would be 12. So the new pressure would be 0.75 atmospheres. I would then just take those two individual pressures and add them together, and that would get me the 2.25 atmospheres. The other option I have to solve this problem is to do PV equals nRT for both gases, get the total number of moles, and then do PV equals nRT again, which is more cumbersome, but it works. So I could do PV equals NR. I'm using this value because I'm using atmospheres as my pressure unit. Temperature 45 to 73 is 318 Kelvin. So I can get the moles of the first one, and then I could do PV equals NRT again and get my second number of moles. I could add those two together, and then I could do P, which is what I'm solving for, V, which is 12, and R, T again to get my, this is 12, to get my total pressure in the container. So there's different ways you can go about solving it. I think doing this one is shorter, obviously, but both would work. Okay, another example, a 40-liter rigid tank contains a gas at 1820 torr, blah, blah, blah. What would be the pressure in the tank if 0.5 moles of gas were added to the cylinder without changing its temperature? So I'm going to show you, again, another way that we could solve this two different ways. So the first way, our beautiful ideal gas law. So pressure is 1820 torr, volume is a 40-liter tank, N is what we're solving for. R, we're going to use 62.36 because our pressure unit is in torr this time. That's on the reference sheet. Temperature is 296 Kelvin. So N is equal to 3.94 moles initially in the container. Okay? Then it says I added another 0.5 moles. It doesn't tell you what the gas is, but it doesn't matter. So now I have 4.44 moles of gas in total, and then I could do PV equals nRT again to get my new pressure. PV equals N, 4.44, R, 62.36, T, 296, where now my pressure is 2048.9 torr. Okay, so that's one way to solve this problem. You cannot use P1, V1 equal over T1, et cetera, because you're changing the number of moles of gas. Okay, the combined gas law works if you just have one quantity of gas and you're just changing the conditions of it. If I'm changing the quantity of gas, I can't use the combined gas law. The other option I would have here, I know the initial pressure of the gas in my container. I can just solve for what would the pressure be of just this gas, PV, because once I put that gas in the 40-liter container, it's going to occupy 40 liters. Moles of gas, that's my 0.5. 62.36 is my R value, 296. The pressure of just this smaller portion of gas would be 230.7 approximately. I can add that to the pressure of the gas that was initially in my container, and I get 2050 torr, which is really close to solving it the other way. So either of those methods would work. The key is to show your math. Here's another sample. 27.4 liters of oxygen, blah, blah, blah. We have oxygen and helium, both pumped into a tank with a volume of 5.8 liters at 25 degrees. So our temperatures are constant here the whole time. Calculate the new partial pressure of the oxygen. So we could do a P1V1 equals P2V2 for both of these gases. So P1, for the oxygen, P1 was 1.3, V1 is 27.4, P2 is what we want to figure out, V2 is 5.81, that's the new container we pumped it into. So P2 is equal to 6.13, that's how I get that first answer. Now I have my helium, my P1 is 2, my V1 is 8.5, my P2 is my unknown, and my V2 is 5.81 because they're both going into the same container. So P2 is equal to 2.93 atmospheres. Now calculate the new total pressure of both gases. I would just add those two together to get my total. You could do a combination of PV equals nRT. You could find the moles of oxygen present. You could find the moles of helium present. You can add those moles together, and then you could do PV equals nRT again using the new volume and new temperature. Combine the moles and then find the pressure. But again, I think this might be an easier way to do it. Another concept that is addressed with Dalton's law of partial pressure, it's related to it, is the idea of mole fraction. It's really just what it says. A mole fraction is a ratio of the number of moles of a given component in a mixture to the total number of moles in the mixture. This is also on your reference sheet. It's this X, which is kind of like, it's Greek letter chi, but just treat it as an X that looks like that on your reference sheet. So the way that it looks on your reference sheet is this. The pressure of a particular gas is equal to the total pressure times the mole fraction of that gas. Mole fraction of that gas is the moles of the gas over the total moles of the mixture. So again, it's on your reference sheet. It's really just plug in and solve. All right, so this one, gaseous, this one's a longer question because now we're involving a chemical reaction. Okay, so gaseous iodine pentafluoride can be prepared by the reaction of solid iodine and gaseous fluorine. So there you have the mole ratio in the equation. A 5-liter flask containing 10 grams of iodine is charged with 10 grams of fluorine. That just means we're throwing 10 grams of fluorine in there. The reaction proceeds until one of the reagents is completely consumed. That phrase right there tells you we're dealing with a limiting reagent problem, limiting reactant, because the starting amounts of two different substances. After the reaction is complete, the temperature of the flask is 125. What's the partial pressure of IF5 in the flask, and what's the mole fraction? Okay, so we're going to first do the limiting reagent part. So we'll start with our 10 grams of iodine. Convert that to moles. Again, do not round off your gram formula masses here. Then I want to take that to moles of IF5. That's the mole ratios in the equation, and that gives me 0.0788 moles of IF5 produced. And then here's my other reactant, 10 grams of fluorine. And my mole ratio. And that gives me 0.105 moles of IF5. Okay, so since the iodine gave me less of a product yield, that means that the iodine was my limiting reagent. So this is the actual amount of IF5 that I can make. Because the other, there's just going to be excess fluorine left over. So now that I know how many moles of IF5 I can make, I can figure out the pressure of the IF5, which is going to be my answer to part A. What's the partial pressure of the IF5 in the flask? So I know I'm solving for pressure. The volume of the flask is 5 liters. The moles of IF5 is 0.0788. The R value, it doesn't give me a specific unit for pressure. In my work, I solved it using atmospheres, so I'm going to use the R value that has atmospheres in it. My temperature of 125 is 398 Kelvin. Remember to convert those. So the pressure of the IF5 is equal to 0.515 atmospheres. When you're doing problems for AP problems, they will tell you what unit to use either in the context of the problem, or the question will say, what's the pressure in atmospheres, so you know what to deal with for your R value. Now, for part B, it says what's the mole fraction of IF5 in the flask? Okay, so now there's going to be fluorine left over because fluorine was the reagent that was present in excess. So we need to figure out how many moles of fluorine are left. How do I do that? I got to figure out how many moles of fluorine I started with, how many moles of fluorine reacted with the iodine, and then subtract to find the moles that are left. So for the initial, so this is all for part B, the initial fluorine would be the 10 grams of fluorine times 1 mole over 38 grams. So my initial moles of fluorine gas is 0.263 moles. Now for the amount used, I have to see how much fluorine reacted with the iodine. So I had 10 grams of iodine that I know I'm going to use up completely. Convert that to moles, to 53.8 grams of iodine. And how much of that iodine reacted with fluorine? Well, that's the mole ratio. Fluorine, 1 mole of iodine. So that gives me 0.197 moles of the fluorine were used. So I start with 0.263, I use 0.197, I subtract those two numbers to figure out how much is left, which is 0.066 moles of fluorine remain. Okay, now the question B is what's the mole fraction of IF5? Well, if I know how many moles of IF5 I made, which I figured out here, that's how many moles I made, here's how many moles of fluorine are left in the tank, I can figure out the mole fraction. So the mole fraction of IF5 is equal to moles of IF5, 0.0788 moles, divided by the total moles in the container, which is the sum of the 0.0788 moles of IF5 and the 0.066 moles of fluorine gas. So that's 0.1448 moles total. When I do that calculation, it is 0.544. There are no units with mole fraction because you're doing moles over moles. So that's that one. A unique kind of situation you could deal with when you're dealing with partial pressures is collecting gas over water. This comes up a lot in gas law problems. You'll see as we work through some free response questions how this shows up a bunch of times. What you can basically do is perform a reaction in some sort of container where gas is produced, and you can collect that gas by bubbling it into an inverted container that was full of water. So basically, as the gas bubbles in, it will displace the water, and then you can measure how many milliliters of gas you collected. Now here's the deal. The gas that's collected up here is going to be the gas that's being produced from that test tube, but also it's going to be mixed with some water vapor because water is constantly evaporating. So to find only the pressure of the gas that you were collecting and getting rid of the water vapor, you have to subtract the vapor pressure of water from the total pressure. The vapor pressure of water is dependent on temperature. You would be given the vapor pressure of water at the temperature that you're dealing with. So here, if I have a volume of a gas mixed with water vapor at 32 degrees Celsius at 742 torr is 1350. So I have some gas mixed with water vapor. That's the pressure that's exerted by the total of the gas and the water vapor in the container. What will be the volume of the gas at 0 degrees Celsius and 760 torr if all the water vapor were removed? The pressure of water vapor at 32 degrees Celsius is 36 torr. Okay, so the first thing we want to do is we want to find just the mass of the gas, and that's just subtraction. So 742 torr was the total pressure in my container, minus the pressure of the water vapor because they behave independently. So the pressure of just the gas is 706 torr. Okay, what would be the volume of the gas at this temperature and pressure if all the water vapor were removed? Well, you should recognize that this is STP. So we have an initial temperature, we have an initial pressure, we have an initial volume, and now they're saying, well, here's the new temperature and the new pressure, what would be the new volume? So we could do a combined gas law problem here. You could do PV equals nRT, solve for moles, and then to PV equals nRT again, using those moles. But I like using this one. So the initial pressure is going to be the pressure of just the gas with the water vapor removed. The initial volume is 1350. The initial temperature, 32 degrees Celsius, is 305 Kelvin. New pressure, 760 torr. New volume is my unknown, and new temperature is 0 degrees Celsius, which is 273 Kelvin. When you solve for V2, you get 1123 milliliters. All right, last example. A sample of KClO3 is decomposed according to this equation. The oxygen produced was collected by displacement of water. So, and you'll be doing this in a lab, so you'll see what I mean by that, when we bubble the gas out. At 22 degrees, total pressure is 754, blah, 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 volume of gas collected. The vapor pressure of water at the temperature is 21 torr. What's the partial pressure of oxygen in the gas collected? So we collected oxygen gas, but it was mixed with water vapor. So the total pressure was 754 minus the pressure of just the water vapor is 733 torr. Okay, subtraction. So that's like actually usually a part of a question, so you get a point for that. Now, how many grams of KClO3 are decomposed? So we know how much oxygen we made. So we can figure out how many moles of oxygen we made because we know the temperature, the volume, and the pressure of the oxygen. Once we know how much oxygen we made, we can work backwards to figure out how much potassium chlorate decomposed to get us there. So our best friend, get this tattooed. Don't get this tattooed on your lower back. You'll never be able to read it. Maybe on your forehead. So the pressure of the gas with just the oxygen was 733. The volume was 0.65 liters. Now you want to make sure when you're using PV equals nRT that you use liters because liters is in the ideal gas constant units. When you're doing the combined gas law, you can use milliliters or liters because they'll end up canceling each other out on each side. Partial pressure was in torr, so we're going to use 62.36 because that's my R value that deals with torr. Temperature is 22 degrees Celsius. which is 295 Kelvin. Well, what did I do here? Oh, N. Sorry, I forgot my moles here. N equals 0.0259 moles. That's how many moles of oxygen were produced, okay, during the reaction. So now I can use the stoichiometry of the reaction, the mole ratios, and work over to grams. So I know I ended up with 0.0259 moles of oxygen. I want to get that over to grams of KClO3. So first step is we have moles of oxygen already, so we can get rid of moles. 3 moles of oxygen on the bottom, 2 moles KClO3 on top. Now I have moles of KClO3. I can get to grams of KClO3 using the gram formula mass, 122.55 grams per mole. Cancel those out, and you get 2.12 grams of KClO3. Look how magical this is. Math is wonderful. I know for a lot of you, the problem is when you see these problems is where do I start? So in class, we're gonna work through problems together. We'll talk through them, and you'll see that there's kind of like there's a standard set of procedures you can take. There's not a lot of routes you can go with these problems, so they're really not too crazy once you get going. Thanks, bye.